some equation which we are simulating in the ANSYS fluent, for example, the linear wave equation. The partial derivative of some parameter, some function by time plus some constant, and the partial derivative of this function by x coordinate is equal to 0 is so-called wave equations. One of the simplest equations is designed to make a linear analysis of partial differential equations and their solutions. Is the wave basically is wave transfer. For example, we have some wave in time, and what is happening, this wave is moving with some velocity a in a positive direction of x. This is our value of the function here. And after some time, this wave moves. Each of these wave point is moving to the same distance. So it basically becomes the same wave but translated. This is the wave equation which is doing this with any u function we define and moving this wave with constant velocity a of all points. As I say, is the simplest equation which allows us to understand about Courant number. So computer is not solving directly in this form. Computer is transforming this equation into an algebraic equation, and it's doing by so-called discretization method. How the discretization method is working? We substitute all the derivatives by their algebraic definition. For example, we have points in space. I will make you several points. This is point of our interest, I, in space. This is the same direction, x. This point I plus 1. Next point, previous point, and the same by time. For example, this is the time layer we are now, time layer, and the next time layer, t plus delta t. We have absolutely same space with absolutely same points in x coordinate, but on the next time step. So it's coordinate I plus 1, I minus 1. And another coordinate, let's call it j, is the time. Of time t we will call j coordinate. Okay. And of time t plus delta t, we will call it j plus 1. So we have such a matrix where points correspond in space and are placed in different time layers. In such way, we can express time derivatives in different ways, but usually the simplest way to express this time derivative will be the following. We will take value of u function on a point j plus 1 in time and point I in space minus the same point in space but previous time step j. We will divide it by delta t, and this will be equivalent representation of time derivative. Okay. Now I will express part with the space derivative. I will put lower because I need more space. So it's a constant A, same speed of the wave, and inside the brackets I will have my space derivative. I will calculate space derivative on the layer where we know parameters, because these parameters let's say it's the initial conditions which we are starting from, where we are starting, so we know all here. And from here for the next time layer we do not know anything yet. So from these points which we are know, I can calculate space derivative. It will be function on j level of time, and let's say I in space, so it's this central point, minus parameter previous on point I minus 1 in space and j by time. And I will divide by delta x. This is our delta x. Okay. And this is our delta t between this and this layer. I will put here between these 2 points. So I will close my brackets, and right part of the equation is equal to 0, as I had before. Yeah, you see, equal to 0. Now I will start to open my brackets and combine parameters. But first, before doing this, I would like to show you everything. Here we may see what parameters are known. We know all on this layer, on the initial layer, we know all parameters. So we know this parameter here, this is constant here, this speed of the wave or velocity of the wave we also know. This is the time step we know. This parameter on the old layer, old time layer, and this parameter on the old time layer we know. So the only unknown here is value of the function on the new layer of time. Actually, this is how we calculate step by step on the new time layer. And I will try to find this. It's one equation with one unknown. Very simple to calculate. So what I will do to calculate this parameter, I will multiply left and right side of the equation by delta t. So I will not have delta t here in the denominator. And after I will add this value to the left and right side of the equation, and I will put this part here to the right side of the equation. So let's do it. Okay, I will write from here. I will choose back my color, and I will write that value of the function which we would like to find, j plus 1 at point I coordinate, would be equal to the following. So I move on and make transformation same time. Just let me see. So it's u on the same coordinate but on the previous time step, and minus will be a. I multiplied all by delta t divided by delta x, and in the brackets I have my u point I j minus u on j minus I minus 1 here. Okay. This simple formula we use to calculate parameters on the new time layer when we know all parameters on the old time layer. This is how transformation of simple differential equation may be done to its algebraic equivalent. There are many ways, many methods to make this kind of transformation with the higher accuracy, with the smaller, lower accuracy, etc. But this is not a question of today's discussion. Today's discussion is the Courant number. What is the Courant number? It's a very simple thing. I will show you it right now. Look this parameter here. What is this? What is the dimension? It's the velocity multiplied by time divided by space. So basically it's the velocity divided by the velocity. Is dimensionless parameter. So this dimensionless parameter for us is nu, which is the Courant number. This is the Courant number. It's dimensionless criteria which gives to us relation between velocity of the flow or velocity of the process change proportional to the time step of integration of our equations of the flow and reverse proportional to the step of space integration of the flow equations. Let's see some examples. I would like to show you the examples with the different values of Courant number. My examples will be the following. First of all, I would like to show you what happens when Courant number is equal to 0. Nu is equal to 0. What does it mean when we look to this definition of Courant number? A cannot be equal to 0 because it's a velocity, or if the velocity of the movement is equal to 0, it means that process is not moving, it's a stationary process which is not changing in time. Then delta x, to make Courant number equal to 0, delta x should be infinite, and this physically is not possible. We cannot have distance between points infinite. So the other possibility is delta t. Delta t is equal to 0. So from here we can have or a equal to 0, so process is not moving, or integration time step equal to 0. So we are not actually integrating anything. We are staying on the same time point. It's equivalent. Or no velocity or same time point is absolutely not progressing. So Courant number equal to 0 or negative, it has absolutely no meaning to us because we are not moving forward in time to integrate our equation from its initial time step to negative time step is not physical absolutely. So it's not possible to simulate back in time because time cannot be negative, and in this case system is not stable. To know what is stable and not stable system is a strict definition, strict mathematical definition. Go to read Anderson, Fletcher, Tannehill, which I upload to the system. We look second example when nu is equal to 1. Very common for us, case. Why is common? Once we are giving to this coefficient value 1, this whole equation is changing. So I will write here, it will be u at point we would like to know on the next time step would be equal to u on the previous time step minus 1, u on the previous time step minus u on the previous point in space. From here we can easily see that we cancel two parameters here, and we have that we can easily see that any parameter on the point of the next time layer will be absolutely same parameter from the previous time layer, from the previous point. Is simply transition from one point to another. So you just transform from one point value to another point. You are not simulating anything. You just translate from one point to another, your solution progresses. It does not degrade. It's a so-called exact solution. It's exact solution because it's not changing in time. It's just translated in time from one point to another without any kind of losses. Another typical value of Courant number for such kind of scheme is when nu is bigger than 1. Nu is bigger than 1. What we have in such case, we can see. For example, okay, something for representative value, I will assume for us nu equal to, okay? And I will rewrite the equation, algebraic equation for nu equal to. What does it mean to us? That velocity of the flow movement multiplied by time step divided by space step is equal to. So I will write that the flow property on some coordinate in next time layer would be equal to flow property on the previous time layer. Here we have minus, right? Minus 2. And here we have parameter on j I minus 1. We can simplify this equation. We can see same property here and here. So I will just subtract one from the other. And we will see that u I minus 1 j minus, I think it's, okay, it will be minus here, right? U ij. So what we are doing, we are basically subtracting one value from another value here. In this case, we have a so-called unstable solution also, similar to what we had for negative Courant number, where solution will degrade from one point to another. Because let's imagine some picture. I will show you one example here. The wave, very simple wave. Okay. This wave, a square wave, for example, one value like this. Okay. This will be value equal to 1, 1, 0, 0. And wave is moving in this direction. And initial time step is this. So if we will try to use formula presented here with Courant equal to, on the next time layer, we will receive the following values. We need to start with the initial conditions, so I will keep the same value of, so this distance is delta t. I will keep the same value of the wave initially, because we need some initial conditions to calculate. And next points I will calculate here based on this formula here. So to calculate on next time point, I need to use previous value minus value on this. So basically this value, right? This value I minus 1, I plus 1, I plus 2. To calculate here, I just need to take a difference between these 2 points. So I will have 0 at this point. What I will have here, I will have 1, because this difference here, 1 minus 0, I will have 1 again. And for this point here, I will need difference between 2 points here. It's 0 because these points are equal. So this was our initial wave at some time step, and this is our new wave or on time step delta t, and the current number equal to. You may find now that is not nice looking wave. Theoretically, how the wave should move if it's a physical wave, if it's a nice calculated wave. Wave should just continue to go, right? And here somewhere should decrease. So it should be a constant wave moving, just moving in one direction with velocity a. What we see here is that we have sudden decrease of the wave because of the formula. So this is why calculation with the current number higher than 1 in this case is absolutely not acceptable, is so-called unstable solution. And if you calculate further, you will see more and more and more problems. For example, you go to calculate on the next time step. Here you will see more and more problems. Let's see this example, how much will be. I will feed with the same initial condition, 1. Then this point, it will be a difference. It will be here. Then this point will be from 0 to 1. It will be already negative. Okay. And this point, it will be also positive. It will be 1. So something like this. You see a next step of simulation. Wave is changed to very strange wave. Somewhere the wave is negative. So calculation with the current number more than 1 is giving us this kind of problem. So your question may be the following. So in Fluent, we can simulate with Fluent with current number 2, 3, 5, 10, 50. And there is no problem. Yes, there is no problem. Because a way of transformation of the equation in derivatives, this initial equation in derivatives, is different from what I wrote you here. The method which is realized in Fluent is different and is not so simple. Let me explain you how Fluent is working and what current number, how the equation is looking. I will rewrite back my initial differential equation. It's du by dt plus a du by dx is equal to 0. And I will write algebraic form of this equation because we already know how to transform different derivatives to algebraic relations, right? We just did it on the previous example. Now will be a bit more complicated. First time derivative, I will write the following way. I will write that my time derivative is ui minus ui on time next minus current. Same way as we had before, plus a. And here will be difference with respect to the previous discussion. Is ui minus 1, j plus 1, j plus 1 divided by delta t, delta x is equal to 0. This is a bit different because now what we have is known value. This we know from the previous time layer, this value, and the velocity we know from the previous time layer. What we do not know is this parameter here, and this parameter here. So we have one equation with the 3 unknown, because all these 3 unknown are on the new time layer. how to solve this equation? Actually, to solve only one equation is not possible. So we need to build the equation system where number of unknown will be equal to the number of equations. In this case, number of unknown will be equal to the number of points in our simulation volume. And the number of equations will be also equal to the number of points in the simulation volume. To give you an example of such equation, I will make some transformations here. I will use properties of my blackboard, and I will just modify what is written here. I will not write you from the beginning. First of all, I will remove delta t from here. I will write it I will multiply all by delta t. Okay. Okay. So delta t is here. Okay. And delta x will be here. So I can remove from here, and this will be inside my bracket. So this piece again is my Courant number. So you see from explicit and implicit scheme, Courant number also exists. Okay, and now I will just rearrange parameters to be more favorable to solve this equation. So you will see how we can obtain the solution. Known value I will put in the right side of the equation, and all unknown values I will keep on the left side of the equation. Okay, let's see what we have similar. We have this parameter and this parameter here similar. So it will be outside of the brackets. I will write here that u I j plus 1 will be in the brackets 1 plus nu. Okay, and then will be minus u I minus 1 j plus 1 multiplied by nu. This nu is from these brackets here. So this is all from unknown, and the known part is u ij. So let's take a look carefully on this equation here, which we just received. We have one unknown right here. We have another unknown here. Near we have a coefficient, another coefficient, which are constant actually, right? And we have another value which is known here. This equation here we can write for any point in space inside our computational volume, because for any point in space we have a point, this point for which we are writing the equation, and we have a previous point for which we are writing equation, except point which is on the very beginning of the computational domain. So we need to set up the value of the boundary condition here. And this point we know from the previous time step. So this value and this value will be unknown. Here all the other are coefficients. This coefficient here, and this coefficient is just a value here. Also important to say that this value is bigger than this value here. So we are having well-defined main diagonal of our matrix equation. So we have actually two diagonal matrix. One main diagonal will be formed by this coefficient here, and additional diagonal will be formed by this coefficient here. So it's two diagonal actually, and all other coefficients of this matrix will be equal to 0. So it will be something of basically coefficients like this. Let me zoom a bit. 1 plus nu, 1 plus nu, and setter at the end 1 plus nu. You see that other values will be equal to 0. 0. Okay. And the second coefficient is nu. And set other coefficients will be equal to 0. So it's well-defined matrix with quite big values on the main diagonal, so it can be efficiently solved, and then it's multiplied by vector of unknown u on the next time layer. This is unknown equal to known vector of the values on the j on the old time layer where we know all coefficients. And from here, if we name, this matrix A, this matrix U, and this vector U, and this vector SB, how can be solved is basically U equal to BA minus 1, right? Where B is vector, A is A minus 1 is the reverse matrix. So we can receive the solution by multiplying this vector and the matrix. This is how Fluent is working. So it's just finding the coefficients of this matrix, here reversing the matrix, and multiplying with a known vector of parameters. Of course, for 4 or 5 flow equations is more complicated, more complex, but the idea is absolutely the same. And the current number is always entering inside these main diagonal and additional diagonals. Depending on the method, it can be 2 diagonal or 3 diagonal, 4 diagonal matrix, different. Depend on which button you click and which method you choose inside the solution. And then this is how the current number is entering the solution. Actually, it's a bit opposite from what you have been asked, that increasing the current number, we increase the velocity of solution, but we decrease the stability. Okay, we decrease the stability. Smaller is current number, better is the stability of the solution. But same time, we have a slower solution. Bigger current number, we receive solution fast, but it can break at some moment, because if we make too big value of current number, it will be unstable. More about stability and stability of computational model is all inside lecture under Santani Hill. And it's a very deep mathematics under this. Is not something simple, and I'm not sure you study at the university this level of mathematics, but you can try to read. It's a functional analysis, quite interesting, and a complex function analysis. Equations of the flow, Navier-Stokes equations, they are not linear. So it will not be such a straight relation. Actually, we do not have an exact solution for Navier-Stokes equation. So in this case, we obtain the optimal current number from the experience. It can be bigger than 1, it can be smaller than 1, it can be much bigger than 1, for example, can be 10, 20, 50 for some simulations. For some simulation can be really small, like 0.1 or 100ths even. You receive a current number from point of view of two things. First of all, you see if your solution is not breaking, if it shows some physical results. Not breaking means it not crashing. It does not show, for example, negative pressure or some strange values of flow properties. And from another point of view, you need to obtain your solution as soon as possible. So you cannot keep very low current number. If you keep it low, it will be super stable, but it will solve for a very, very long time. So you need basically a huge time of simulation, which we cannot have. Okay. So this is these two parameters. We choose between time of solution and stability of the flow. If the flow is stable enough and you are satisfied with the flow results, you keep this current number. But for every different task, this value is different. It cannot be known before you do simulation. You can know it from your previous experience, for example. But when you switch from one task to another task, this value is changing. So try with different current numbers, try to have as big as possible until your flow starts to crash, and then you will know the physical limit of current number that can be used. After you make simulation, make validation with experimental data, and you will know if this current number you used was compatible with the result you obtain. So only by experiment or by experience. It's interesting. It's an interesting question, which has to be studied only experimentally. Also, if you do not have time to make experiments, you can go to see in the literature for many classical works, this current number is already defined, depending on what is your geometry, what are your conditions of the flow, what are your models. They suggest different values of current number for good quality solution. Also another way. So literature review, personal experience, work. Okay, I hope this is enough to understand more or less. Question of current number is not that simple as it looks like. It's a big story. Mm-hmm. Yeah. Today chat is not working well. I don't know why. I do not see many questions. Maybe because it's overloaded with many classes. Coeficiente de momento e quarter-chord para folio que eu escolhi tem problema? No, of course there is no problem of 1/4. You just needed to do simulation and put your origin of coordinates in the point of 1/4 chord, as same as I show in the example, actually on YouTube. These simulations I make for YouTube, they are all made for 1/4 chord momentum coefficient, so you can easily do this. What you need to do, the most important point, put origin of coordinates in exactly the point where you would like to measure the moment. Okay, and then you do not need to do any additional operations to recalculate the moment coefficient. So the momentum coefficient you will receive is already on 1/4 chord. It's very common thing. There are different ways to simulate, right? To put origin of coordinates in the leading edge, to put on the trailing edge, to put origin of coordinates on 1/4 chord, which I show how to do. And then you will receive corresponding values of momentum coefficients. But it's also always possible to calculate momentum coefficient for any point if you use corresponding formula for momentum coefficient. Just a moment, I can try to see to say what is exactly the formula. It's somewhere at the beginning of the book. It's 122. 122 is the relation between momentum on leading edge, 1/4 chord. So basically, if you receive forces you can calculate momentum independently, right? By formula, you do not need to use Fluent, for example, to calculate momentum. You just put coordinates you want and the forces you already have. So just multiply forces by distance and you calculate the momentum.